Last time we had talked about general properties of discrete random variables. So if our random variable is denoted by x, we studied things like the probability mass function, the cumulative distribution function, e of x and variance of x, which represent expected value, and the variance, which we get standard deviation. All of these things are general concepts which are going to get returned to, but now we shift our focus and we start studying specific mass functions in specific situations. So we're going to talk about specific probability models for discrete random variables. So today in particular, we are going to talk about one that's really important and very common. And so some experiments have only two outcomes at each stage. And so the most common one is a coin flip, right? It's either heads or tails. You can think about opening a valve. If you open a valve, it's either open or it's not. Okay. Many things are binary in this sense, 0 or 1. And so sometimes this is called a Bernoulli trial, when all you have is two outcomes, success or failure. Okay? So we are going to talk about an experiment that uses a Bernoulli trial at every stage. So we are going to talk about experiments that are in what we call the binomial setting. And when something's in a binomial setting, what we've got is a fixed number of Bernoulli trials. So a fixed number of trials or stages that just have two outcomes. These trials are independent of each other. So mathematically, we understand that independent events like this, there's no influence on the probability. And that means that we have to have a fixed probability of success in each trial. So if we have all of these things, then we have an experiment that's in the binomial setting. So a very easy example is then just to say, well, let's flip a coin 10 times. And let's study the number of heads that we get. Okay. This is very much an example of a binomial experiment or something in the binomial setting. And so chapter 3.1 is interested in experiments in this form. So what we want to do is we want to come up with a general, or we want to generalize for the following. We're going to let X represent the number of successes in N trials of this experiment. So if I flip a coin 10 times and I call success getting a heads, then note that the number of successes could range anywhere from 0 up to the full number of trials. So again, I flip a coin 10 times, I could get 0 heads, 1 head, 2 heads, all the way up to and including 10. I can't get more than 10, and I can't get less than 0. Okay? So this is for any binomial setting. Okay? What we would like to do is to find the probability mass function for this random variable X. And to try to show this to you, I am going to go through an example. And another way of referring to this is we're going to say that the probability mass function for this random variable is what we call the binomial distribution. So on the PDF file that I've attached to these video notes, I have an example about mortality tables. So it's kind of a grim but realistic example. So these mortality tables are something that are used by actuaries to set insurance premiums and insurance rates and things of that sort. And the first thing we'd like to know is, okay, is this type of thing in the binomial setting? And in this particular case, we have Bernoulli trials. And the answer is yes, we do, because success means that you live to 65 or you don't. That's what we're going to call success. We have a fixed number of them. We are going to say that the total number of trials is 3 because we choose 3 people. We're going to assume that it's independent because we're going to assume that choosing people at random is our realistic, real-world equivalent of making things independent. These 3 people chosen at random don't necessarily have anything to do with each other. They're not related. They may not have the same genetic factors or health factors or environment or any of the sort. And finally, the probability of success, we are going to call little p, and this is given as 80%. And so we are going to assume that that applies to every person in this binomial setting. So yes, this type of situation can be modeled with a binomial setting. So what we want to do is our usual thing of figuring out all of the outcomes. At stage 1, you choose person 1. Either that person lives to be 65, so we're going to call that S for success, or they don't, F for failure. Stage 2, you have the same 2 outcomes, and the same thing in stage 3. So this is a 3-stage experiment. Now I'm going to be lazy about how I write the outcomes. SSS will stand for success, success, success. There's intersections technically between them. That means all 3 of the people chosen live to be 65. SSF, and if we just go through and we list everything off, we will come up with all of the outcomes. And so this is nothing new. This is exactly what we have done in the past. Okay. Now, to construct the mass function, remember that we are trying to build a table as follows. X, this random variable, stands for the number of successes in each outcome. And so what we need to do is we need to start enumerating things. Now, I'm hoping that you can see there is only one outcome where the number of successes is 0. So 0 is an option. And remember that the number of successes can range anywhere from none to all of them being successes. Okay. In each case, number of successes as 3 and number of successes as 0, there only seems to be one outcome. And so that's fine. We're going to deal with that. The most important contribution to a mass function here is the probability values. And this is where the other 2 pieces of information in the binomial setting come in. You're given a probability of success for each stage. Because it's independent, you know that you can just copy and paste all of those values to each stage. Each stage does not have any memory of the prior stages. That's where the independence comes in, and the fixed number means it's easy to deal with what we've got. So, if we go through and we calculate the probability of failure, this is a 3-stage event, and all we need to do is use the multiplication rule. In this particular case, we've got 0.2 cubed because we've got 3 branches of 0.2, 0.2, 0.2. Now, it's exactly the same thing that happens on that top branch, except that the value of probability that we're using is 0.8. And so this number gets cubed. And if we take a look at what these values are, you should be able to see or you can take a calculator, whatever the value is, 0.008 for this contribution. And in the other circumstance, it works out to be a similar number. I'm just flipping through, trying to find it. My mistake. Sorry about this. This one comes out to be 0.512. Okay, now the real question where the other work comes in is the other branches. If I'd like to figure out the probability of success for one, and so I need to enumerate all of the situations where I just have one success. And there are 3 of them. So if I follow down, there's something that's common about each one of these. So in each branch of the situation where I have one success, there is only one value of 0.8, and there are 2 values of 0.2. So each branch here has a 0.2 to the power of 2 multiplied with a 0.8 to the power of 1. But there are 3 of these branches. Now, finally, if I'm interested in the case of 2 successes, I've got 1, 2, 3 of these outcomes, and I calculate things in exactly the same way. Each branch, if you take a look at any one of the branches leading to 2 successes, there are 2 S's and 1 failure. So that means I will have 0.8 to the power of 2 multiplied with 0.2 to the power of 1. Now, if it comes time to crunch these numbers, crunching the numbers is not really a big deal. You can take a calculator and hammer them out. So for instance, that one is going to be 0.096, whereas this one is going to be 0.384. And so what we have done is we have now constructed this probability mass function. So it's a table, and this table is easily constructed. We'll have 0, 1, 2, 3, and we can plug in all of these numbers: 0.008, 0.096, 0.384, 0.512. Now, if it comes time to ask certain questions, like what is the probability that at most one person survives, this is straightforward because this talks about the random variable, and it's saying, oh, my mistake, that you can't have any more than one person. So this would simply be the situation where you've got probability of x is 0 plus probability of x equals 1, and you could just add these 2 values. So it's pretty straightforward in that sense. Similarly, if you wanted to do something like find the probability that at least one person survives, this is a statement kind of like this: x is greater than or equal to 1. Since your sample space contains only the outcomes 0, 1, 2, or 3, you could use the rule of complements and reduce this problem down to a 1 minus p of x equals 0. And again, getting the numbers here are pretty straightforward. But we don't want just the numbers. What we want to be able to do is generalize this. And so in the next video, we're going to talk about how can we generalize this